What if everything you thought you knew about reality was only half the story? Picture a cat seemingly ordinary, resting inside a sealed box. But here's the twist. According to the bizarre rules of quantum mechanics, until you open that box, the cat is neither alive nor dead. It exists in both states at once. This is Schrödinger's famous paradox, a thought experiment that cracks open the door to a universe far stranger than we ever imagined. And this is just the beginning. The deeper we dive into the quantum world, the more reality seems to unravel, revealing layers of possibility that defy our everyday intuition. For decades, scientists and philosophers have wrestled with the mind-bending implications of quantum theory, a framework so powerful it shapes our understanding of everything from the tiniest particles to the vast expanse of the cosmos. But with every answer comes new questions, each more perplexing than the last. Could there be infinite versions of you, living out alternate lives in parallel universes? Is time itself an illusion woven from the fabric of quantum entanglement? These aren't just ideas from science fiction. They're serious theories debated by leading minds, each one pushing the boundaries of what we consider real. And today, we're about to explore 30 of the most astonishing among them. This journey won't just challenge what you think you know, it will stretch the limits of your imagination. From the holographic principle suggesting our universe might be a projection, to the eerie phenomenon of quantum superposition where particles exist in multiple places at once, we're about to venture into a realm where the rules of classical physics no longer apply. But don't worry, you won't need a degree in quantum mechanics to follow along. We'll unravel these ideas step by step, blending cutting-edge science with the profound philosophical questions they inspire. So if you're ready to question the very nature of existence, to peer into the hidden workings of the cosmos, then let's begin. Because the quantum world isn't just strange, it's the key to unlocking the universe's greatest mysteries. What if every choice you've ever made, from what you ate for breakfast to the career path you chose, didn't just shape your life, but created entirely new universes where alternate versions of you took every possible path? That's the radical proposition of the many worlds interpretation, a theory dreamed up by physicist Hugh Everett in the 1950s. While traditional physics treats quantum events as probabilities, like a coin toss where the coin is both heads and tails until you look, Everett suggested something far wilder. He argued that the universe doesn't settle on one outcome. Instead, it splits into multiple branches, each one realizing every possible result simultaneously. Take the famous double-slit experiment, where particles like electrons are fired at a barrier with two openings. Classically, you'd expect them to pass through one slit or the other, creating two distinct bands on a detector screen. But in reality, they create an interference pattern, as if each particle passes through both slits at once, behaving like a wave. When scientists try to observe which slit the particle actually takes, though, the interference vanishes. The particle acts like a single, definite object. The many worlds interpretation offers a startling explanation. Both outcomes happen, but in separate, freshly spawned realities. In one universe, you observe the particle going left. In another, you see it go right. The interference pattern, that's the ghostly echo of all those branching worlds overlapping before they diverge. This idea forces us to confront profound questions about free will. If every decision spawns infinite versions of you, are you truly in control, or are you just one thread in an endlessly unfolding tapestry of possibilities? Some argue this makes choice meaningless. Every option is taken somewhere. Others see it as liberating. No path is truly closed, just explored in another reality. And if that sounds like science fiction, consider this. Variations of the many worlds interpretation are now taken seriously by many quantum physicists, not as fantasy, but as a mathematically consistent way to explain the bizarre behavior of particles. Yet for all its elegance, the theory leaves gaps. How do these branches form? Why can't we perceive them? Some suggest the splits happen at the quantum level, too subtle for our macroscopic senses. Others propose that parallel universes might interact in ways we haven't detected yet. What's clear is that if Everett was right, reality isn't just stranger than we imagine. It's stranger than we can imagine, with every moment birthing countless new worlds, each humming along unseen, just beyond the edge of our perception. Now imagine this unsettling scenario. You're sitting in front of a device linked to a quantum trigger, a mechanism that has a 50% chance of releasing a deadly pulse with each activation. Every time you press the button, the quantum outcome splits reality. In one branch you live, in another you die. Yet no matter how many times you press it, from your perspective, you always survive. This is the chilling thought experiment known as quantum suicide, and it leads us straight to one of the most provocative theories in modern physics, quantum immortality. At its core, this idea suggests that consciousness isn't just a passive observer but an active participant in shaping reality. Proponents argue that your subjective experience can't include moments where you cease to exist because, well, you wouldn't be around to experience them. So in a branching multiverse, your awareness naturally follows the timelines where you remain alive, no matter how improbable those paths might seem. To you, it feels like luck or even destiny, but statistically, there's always at least one universe where you improbably dodge every bullet, survive every disaster, and live on. Critics counter that this smacks of solipsism, the belief that only one's own mind is sure to exist. If every observer's consciousness carves out their own preferred reality, does objective reality even exist? Or is the universe just a patchwork of subjective experiences, each convinced of its own continuity? The debate forces us to confront deep questions about the nature of existence. Is death an absolute endpoint, or merely a transition we never witness because our awareness hops to the nearest living version of ourselves? Interestingly, quantum immortality doesn't promise eternal youth or health, just the persistence of consciousness. You might still age, suffer injuries, or deteriorate, but your awareness would always follow the path where you cling to life, even under astronomically low odds. Picture a car crash survivor who walks away unscathed against all logic, or a terminal patient who outlives every prognosis. Are these miracles, or just the visible threads of a far weirder cosmic truth? The theory also blurs the line between science and philosophy. If consciousness truly biases reality, could it explain why we perceive a stable, classical world at all? After all, quantum mechanics suggests particles exist in fuzzy superpositions until observed. Maybe our survival-oriented perception collapses probabilities into a reality that feels continuous, a universe that, by design, never lets us see behind the curtain. Of course, quantum immortality remains untestable by its very nature. You can't confirm the existence of branches where you died, and those who might have disproven it aren't around to report back. But as a mind-bending lens on existence, it challenges us to rethink not just how we live, but what it even means to be alive in a quantum multiverse where every possibility plays out somewhere. And that's a puzzle far stranger than fiction. But what if the three-dimensional world we experience, the depth of a forest, the curve of a mountain, even the vastness of space itself, is nothing more than an illusion? Enter the holographic principle, a theory so radical it suggests our universe might be a two-dimensional surface projecting a three-dimensional reality, like a cosmic version of a credit card hologram. This idea didn't come from science fiction, but from one of the most enigmatic objects in nature, black holes. Leonard Susskind and Nobel laureate Gerard T. Hooft first proposed this mind-bending concept in the 1990s, inspired by a peculiar paradox. When matter falls into a black hole, it vanishes forever, seemingly erasing information, a direct violation of quantum mechanics, which states information can never be destroyed. But here's the twist. Black holes also emit Hawking radiation, slowly evaporating over time. So where does the information go? Suskind's breakthrough was realizing it might never have entered the black hole at all. Instead, it could be encoded on the event horizon, the black hole's two-dimensional surface, like a celestial hard drive. Every particle swallowed leaves a pixel on this boundary, preserving the data in a form we can't yet decode. Extend this idea to the entire universe, and things get even wilder. If a black hole's interior can be described entirely by information on its surface, could the same be true for our cosmos? The holographic principle argues yes, that everything we see, touch, and experience might be a projection from a flat, distant boundary we'll never perceive. Think of it like watching a 3D movie. The images seem to have depth, but they're all generated from flat data on the projector's film. In this case, the film could lie at the edge of the observable universe or even woven into the fabric of spacetime itself. This theory doesn't just solve the black hole information paradox, it could be the missing link between quantum mechanics and gravity. Einstein's general relativity describes gravity as the curvature of spacetime, while quantum mechanics governs the subatomic world. But the two frameworks refuse to mesh, a problem that stumped physicists for a century. The holographic principle offers a way out. If gravity emerges from quantum interactions on a 2D surface, it might not be a fundamental force at all, but a side effect of deeper, flat reality. Critics point out we lack direct evidence. No one's found the universe's projector screen. Yet experiments like Fermilab's holometer have searched for telltale quantum fuzziness that might betray our holographic origins. And if the principle holds, it rewrites not just physics but philosophy. Are we living in a simulated universe? Is free will just part of the code? For now, the answers remain out of reach, shimmering like a mirage on the horizon of human understanding. But one thing's certain, if the holographic principle is true, reality is far stranger and far flatter than we ever dreamed. Einstein famously called it spooky action at a distance, a phenomenon so bizarre it challenged the very foundations of physics. Quantum entanglement, the strange link between particles that instantly influences one another no matter how far apart they are, seemed to violate relativity's cosmic speed limit. Nothing can travel faster than light. Yet here was nature defying that rule with what appeared to be instantaneous communication. For Einstein, this wasn't just puzzling, it was unacceptable. He spent years arguing that quantum mechanics must be incomplete, that there were hidden variables quietly guiding these particles behind the scenes. But what if reality was simply stranger than even Einstein could accept? Take two entangled electrons, for example. When created together, their properties like spin or polarization become mysteriously linked. Measure one, and its partner instantly assumes the opposite state, whether they're across the lab or on opposite sides of the galaxy, the eerie part. This happens faster than light could travel between them, as if space and time don't apply. Einstein saw this as proof that quantum theory was flawed, since no signal could bridge that gap without breaking relativity's rules. But in the 1960s, physicist John Bell devised an experiment to settle the debate once and for all. His equations showed that if hidden variables existed, entangled particles would correlate only up to a certain limit. Quantum mechanics, however, predicted stronger correlations. Decades later, with precise lasers and detectors, scientists confirmed Bell's predictions. Entangled particles do violate those limits. There are no hidden variables, just genuine, non-local connection that defies classical intuition. This revelation cracks open wild possibilities. Could we harness entanglement for instant communication across interstellar distances? The answer for now is a frustrating no. While the particles sink faster than light, the information they carry can't be controlled or decoded without classical signals, which obey relativity's speed limit. You might know your entangled particle state instantly, But to use that knowledge, you'd still need to call your collaborator on a slow, old-fashioned radio. Yet the implications run deeper than practicality. Entanglement suggests that at a fundamental level, the universe isn't made of isolated parts, but of deeply interwoven relationships. Particles separated by light years behave as a single system, as if the cosmos is stitched together by invisible threads we're only beginning to glimpse. Recent breakthroughs push this further. Chinese satellites have beamed entangled photons over record distances, while lab experiments entangle not just particles but entire clouds of atoms. Some theorists even propose that spacetime itself emerges from a vast quantum network of entangled connections, meaning what we call distance might just be a lack of entanglement between objects. It's a haunting thought. The solid, separate world we experience could be an illusion, with everything secretly linked in ways that make here and there meaningless at the quantum level. Einstein's spookiness has become one of physics' most profound truths. Far from a flaw, entanglement reveals a universe more interconnected than we ever imagined, where particles whisper to each other across the void, and reality itself might be built from relationships, not things. And that's a mystery far stranger than any hidden variable. What if the universe's quantum quirks aren't glitches in reality, but artifacts of its source code? The simulation hypothesis takes the strangeness of quantum mechanics and flips it on its head, proposing that the probabilistic, pixelated nature of our universe might be evidence we're living inside an advanced digital construct. Philosopher Nick Bostrom laid the groundwork with his infamous trilemma. At least one of these statements must be true. 1. Almost all civilizations go extinct before reaching technological maturity. 2. Mature civilizations lose interest in creating ancestor simulations. Or 3. We're almost certainly living in one. Think of quantum indeterminacy as the universe's way of saving processing power. In a simulation, rendering every particle's exact state in real time would require unimaginable computational resources. But if certain details only resolve when observed, like a video game loading textures only when a player looks, it drastically reduces the workload. This could explain why particles exist in fuzzy superpositions until measured. The simulation doesn't bother calculating definite properties until absolutely necessary. Even the Planck length, the smallest meaningful unit of space, might be the pixel size of this cosmic resolution. Critics argue this is untestable metaphysics, but some physicists propose ways to check. If the universe is coded, there might be detectable limits to its precision, like rounding errors in a calculator. Others suggest looking for repeating patterns in cosmic rays, akin to the repeating textures in a poorly rendered video game. So far, no smoking gun, yet the hypothesis gains traction because it reframes quantum oddities not as bugs but as features. Wave function collapse, just lazy loading. Entanglement, data packets syncing between distant subsystems. Even the holographic principle fits neatly. A 2D boundary storing 3D information mirrors how graphics engines compress data. But here's the twist. If we're in a simulation, could our own quantum experiments be probing its boundaries like characters in a game discovering their world's engine? And if so, what happens when we find the edges? The simulation hypothesis doesn't just blur science and philosophy. It turns existence into the ultimate escape room, where every quantum clue might lead us closer to the exit. Here's something that will make you question whether reality exists when you're not looking. In the quantum world, particles don't just behave differently when observed. They seem to choose their behavior based on whether anyone's watching. This is the observer effect, a cornerstone of the Copenhagen interpretation, which states that a particle's wave function, a mathematical description of its possible states, collapses into a definite reality only when measured. Until then, it exists as a haze of probabilities, a ghost of all possible outcomes. The classic double-slit experiment reveals this phenomenon in action. Fire particles like electrons at a barrier with two slits, and over time, they create an interference pattern on the detector screen, a telltale sign that each particle behaved like a wave, passing through both slits simultaneously and interfering with itself. But the moment scientists place a detector to observe which slit the particle actually travels through, the interference pattern vanishes. The particles suddenly act like well-behaved little marbles going through one slit or the other. It's as if the particles know they're being watched and change their behavior to oblige. This raises a dizzying question: does consciousness itself play a role in shaping reality? The Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg, suggests that measurement, whether by a machine or a human, forces the quantum system to pick a state. But here's where things get murky. What counts as an observer, a camera, a cat, a human mind? Some interpretations, like von Neumann-Wigner's, take it a step further, proposing that consciousness is the ultimate catalyst for wave-function collapse. If true, the universe might not just be, it might become because we're here to see it. Critics push back hard. They argue that observation in quantum mechanics simply means interaction with any macroscopic system, not literal human awareness. Photons bouncing off an electron to measure its position can collapse the wave function just as effectively as a scientist scribbling notes. This less mystical view, sometimes called quantum decoherence, explains collapse as the particle's entanglement with its environment, a chain reaction that leaks quantum weirdness into the wider world, forcing definite outcomes without invoking consciousness. Yet the mystery lingers. Even if consciousness isn't required, the fact that measurement changes reality at all is profound. It implies that the universe isn't a static stage but an interactive performance where the act of looking shapes what's there. Maybe this is why some physicists joke that quantum mechanics isn't just a theory, it's a haunting. Because every time we try to pin reality down, it slips through our fingers like smoke, leaving us to wonder, is the cosmos a place or a process? And if the latter, who or what is running the show? Imagine a world where reality isn't fixed but constantly being voted into existence. That's the core idea behind quantum Darwinism, a theory developed by physicist Wojciech to solve one of quantum mechanics' greatest puzzles. How does the fuzzy, probabilistic quantum world give way to the solid, predictable reality we experience every day? At the quantum level, particles exist in superpositions, multiple states at once until measured. But why don't we see tables, cats, or planets in such blurred states? Why does reality seem so stubbornly objective? The answer might lie not in some mysterious collapse of the wave function, but in something far more mundane, the relentless gossip of the environment. Every particle is constantly bumping into photons, air molecules, and other bits of its surroundings. According to quantum Darwinism, these countless interactions act like a chorus of witnesses, all redundantly recording the same information about the particle's state. Over time, certain quantum states prove more resilient to this environmental scrutiny, while others fade away, not because consciousness observes them, but because they survive the Darwinian struggle of being constantly measured by their surroundings. The states that persist are the ones we come to call real. It's as if the universe itself is conducting a continuous opinion poll, and only the most popular outcomes stick around long enough for us to notice. This theory elegantly bridges the quantum and classical worlds. Take Schrödinger's cat. Normally, we think of it as both alive and dead until someone opens the box. But quantum Darwinism suggests the cat's fate is decided long before a human peeks inside. The air molecules bouncing off the cat, the radiation from its body heat, even the faint tremors of its whiskers, all these interactions constantly measure its state, reinforcing one outcome over the other. By the time you lift the lid, the environment has already broadcast the result so widely that it's effectively frozen into objective reality. Critics argue this still doesn't fully explain why we perceive a single, definite world instead of a mosaic of possibilities. But supporters counter that quantum Darwinism offers something rare in quantum foundations, a testable mechanism. Experiments with quantum dots and other systems have shown how environmental interactions can prune away fragile quantum states, leaving behind the robust classical ones. It's a subtle process, like how a river smooths a jagged rock over time, not by design, but through countless tiny collisions. What's truly profound is how this theory reframes our place in the universe. We're not special observers collapsing reality with our minds. We're just latecomers to a conversation that's been raging since the Big Bang. Every photon that scatters off an object, every breeze that rustles a leaf, is casting a vote in the cosmic election of what gets to be real. And in that endless chatter, objective reality emerges not as a decree from physics, but as a consensus built one interaction at a time. We often think of time as an unstoppable river, flowing from past to future at a steady pace. But what if it's not a fundamental part of the universe at all? What if time is just an illusion emerging from something far stranger, quantum entanglement? This radical idea, championed by physicist Carlo Rovelli, suggests that time isn't woven into the fabric of reality. Instead, it's a side effect, a mirage created by the intricate dance of entangled particles. Rovelli's thermal time hypothesis flips our intuition on its head. Imagine a universe where there are no clocks, no ticking seconds, just a vast network of quantum connections. In this view, what we perceive as the passage of time is actually the result of particles interacting and entangling with one another. The flow of time emerges from these relationships, much like how temperature emerges from the collective motion of molecules. You can't point to a single molecule and say, this one is temperature. Similarly, Rovelli argues you can't isolate time as a standalone entity. It's a story we tell to make sense of change, not a feature of the universe itself. This leads to some mind-bending implications. If time isn't fundamental, then the Big Bang might not be the beginning of time, just a point where our current understanding breaks down. Picture a room filled with mirrors reflecting each other infinitely. There's no single first reflection, they all depend on one another. In the same way, the universe's earliest moments might not be a linear starting gun, but a tangled web of quantum correlations where before and after lose meaning. Critics ask, if time isn't real, why does it feel so concrete? Rovelli's answer lies in thermodynamics, the study of heat and disorder. The arrow of time, the reason we remember the past but not the future, could simply be the universe's tendency toward disorder. A broken egg never unscrambles, not because time forbids it, but because entropy makes it statistically unlikely. In this framework, our experience of time is just the universe's way of counting possibilities, not an intrinsic flow. Experiments are starting to test these ideas. Quantum systems can be engineered to behave as if time doesn't exist, with particles remaining in superposition indefinitely unless disturbed. Some theorists even suggest that black holes, where gravity warps spacetime to extremes, might be windows into a timeless reality. If they're right, then our daily sense of time, the alarms, the deadlines, the aging might be nothing more than a cosmic sleight of hand, a trick played by quantum entanglement on a grand scale. The thermal time hypothesis doesn't just rewrite physics, it reshapes philosophy. If time is emergent, not absolute, does free will still make sense? Is the future already written in the quantum connections we can't yet decode? For now, these questions hover at the edge of science, hinting at a universe far more interconnected and far less linear than we ever imagined. One where time itself might just be the universe's most persuasive illusion. John Wheeler, one of the 20th century's most visionary physicists, once proposed that the universe might not just be observed, it might be built by observation itself. His daring it-from-bit hypothesis suggests that every particle, every force, even spacetime itself, ultimately boils down to information. Not just any information, but answers to yes or no questions posed by observers. In this radical view, reality isn't a pre-existing stage. It's a cosmic game of 20 questions where the act of measurement doesn't just reveal the world, but actively conjures it into being. This idea finds eerie support in Wheeler's delayed choice experiments, thought experiments that twist causality into knots. Picture a photon traveling toward a beam splitter where it can take one of two paths. Normally, placing a detector after the splitter forces the photon to choose a path behaving like a particle. Remove the detector and it behaves like a wave, taking both paths simultaneously. But here's the twist. Wheeler realized you could wait until after the photon has already passed the splitter, or so classical intuition says, before deciding whether to insert the detector. Astonishingly, the photon's behavior seems to retroactively change based on that future choice. It's as if the universe is editing its own history to stay consistent with how we eventually observe it. This isn't just philosophical hand-waving. Modern quantum optics labs have confirmed versions of this effect. In 2007, scientists performed a cosmic-scale delayed choice experiment using light from distant quasars that had traveled billions of years before Earth existed. By choosing how to measure those photons now, they influenced whether the ancient light behaved as particles or waves, retroactively shaping events that predated our planet. If that doesn't unsettle your sense of time, nothing will. Critics argue this doesn't prove consciousness creates reality, only that quantum systems remain unsettled until measured by something, even a machine. But Wheeler's deeper insight was about the universe's self-synthesizing nature. Imagine a vast cosmic Wikipedia where every edit changes the article's history and every reader becomes a co-author. In this participatory universe, the Big Bang might not be the first chapter, but a cascade of observational choices stretching backward and forward in time, weaving reality as it goes. The implications are staggering. If observation shapes existence, could the universe have fine-tuned itself for life by anticipating future observers? Are we, in some small way, completing the cosmos simply by being here to see it? Wheeler's vision blurs the line between physics and metaphysics, leaving us with a humbling thought. Reality might not be something we find, but something we finish, one measurement at a time. What if space-time itself isn't smooth and continuous, but made of tiny, indivisible chunks like the pixels on a screen, but trillions of times smaller? That's the startling premise of loop quantum gravity, a theory that dares to rewrite Einstein's vision of gravity by treating space-time as a fabric woven from finite quantum threads. While string theory imagines tiny vibrating strings as nature's fundamental building blocks, loop quantum gravity takes a radically different approach. Instead of adding extra dimensions or unifying forces, it asks a simpler, deeper question. What if gravity isn't a force at all, but the emergent property of spacetime's quantum structure? Picture the universe not as an empty stage, but as a dynamic network of intersecting loops, a cosmic spiderweb where each thread carries a discrete quantum of area or volume. These loops don't exist in space, they are space. When they intersect, they create nodes representing tiny grains of spacetime, with the entire universe emerging from their connections. This granularity isn't just theoretical, it offers a stunning solution to one of physics' greatest headaches, the singularity at the heart of black holes. In Einstein's relativity, crushing gravity warps spacetime infinitely at a black hole's core, creating a point where physics breaks down, but loop quantum gravity suggests a different fate. As matter collapses, it reaches a point where spacetime's quantum structure can't be squeezed further. Instead of a singularity, you get a bounce, a cosmic rebound where the collapsing matter springs back outward, potentially birthing a new universe. The contrast with string theory is striking. String theory seeks a theory of everything by unifying all forces within a higher dimensional framework, often requiring abstract mathematical landscapes. Loop quantum gravity, meanwhile, stays firmly in 4 dimensions, focusing solely on quantizing spacetime itself. It's a minimalist dream, no hidden dimensions, no parallel brains, just spacetime revealing its atomic nature when probed at the smallest scales. Experiments could one day test these ideas. If spacetime is granular, ultra-high-energy cosmic rays might stumble upon its pixels, subtly altering their behavior. Some models even predict that the universe's quantum structure could leave faint imprints on ancient light from the Big Bang, detectable in future telescopes. For now, the theory remains a breathtaking work in progress, a reminder that the fabric of reality might not just be warped but woven, stitch by quantum stitch, into existence. Imagine a cosmic faucet left running forever, endlessly spawning new universes like soap bubbles in an infinite bathtub. This is eternal inflation, the idea that our entire universe might be just one accidental bubble in a frothing multiverse, each with its own wildly different laws of physics. The theory builds on Alan Gough's groundbreaking inflation model, which explains why our universe is so remarkably smooth and flat. But here's the twist: inflation doesn't have to stop everywhere at once. While our bubble universe cooled into galaxies and planets, other regions of spacetime could still be inflating exponentially, birthing fresh bubbles where the rules of reality are nothing like ours. Some of these bubbles might have stronger gravity, making stars burn out in seconds. Others could have no weak nuclear force, preventing atoms from forming at all. A select few, by sheer statistical luck, might have just the right constants for life, which solves the fine-tuning problem without invoking a cosmic designer. If infinite bubbles exist, it's no surprise we find ourselves in one where physics allows our existence. It's like walking into a library with every possible book. Of course, you'll stumble upon one written in your language eventually. But this elegant solution comes with a catch. If other bubble universes are forever beyond our cosmic horizon, how could we ever prove they exist? Critics argue this makes eternal inflation dangerously close to metaphysics, a beautiful idea that might never be testable. Yet some physicists aren't giving up. They hunt for bruises on the cosmic microwave background, subtle imprints where our bubble might have collided with another in the early universe. Others suggest that advanced civilizations could engineer universe-scale experiments to probe the multiverse's structure, the most haunting implication. Even if we confirm eternal inflation, we'll likely never know what's inside those other bubbles, whether they're barren wastelands of failed physics or thriving with alien civilizations living under laws we can't fathom. Our universe might just be a single note in an endless symphony of realities, playing to an audience we'll never meet. What if human consciousness isn't just a byproduct of brain chemistry, but a quantum phenomenon woven into the very fabric of reality? This is the bold claim at the heart of the Penrose-Hameroff theory of quantum consciousness, a hypothesis that bridges neuroscience, quantum physics, and philosophy in ways that challenge everything we think we know about the mind. At its core, the theory suggests that our ability to think, feel, and make choices might arise from tiny quantum vibrations inside the brain's microtubules, structures so small they're measured in billionths of a meter. Microtubules act like scaffolding inside neurons, maintaining their shape and transporting molecules, but physicists Roger Penrose and anesthesiologist Stuart Hameroff propose they do far more. They argue these tiny tubes could host quantum states where proteins called tubulins exist in superpositions, oscillating between multiple configurations at once until collapsing into definite states. Each collapse, they suggest, could correspond to a moment of conscious experience, a fleeting now in the stream of awareness. Even wilder, these quantum processes might connect to the universe's fundamental geometry, with consciousness arising from spacetime itself at the tiniest scales. The implications for free will are staggering. If our decisions involve quantum indeterminacy, they wouldn't be fully predetermined by prior physical causes. Instead, choices might emerge from a dance between brain biology and quantum randomness, a space where genuine novelty could enter the universe. Imagine facing a dilemma. Your brain's microtubules hover in superposition between possible outcomes until the moment of decision, when one path crystallizes into reality. This wouldn't be randomness, but a non-algorithmic process Penrose calls objective reduction, where consciousness taps into physics beyond current computation. Critics fire back hard. Many neuroscientists argue the brain is simply too warm, wet, and noisy for delicate quantum states to persist long enough to matter. Decoherence, the tendency of quantum systems to collapse when interacting with their environment, should obliterate such effects almost instantly. Even proponents admit the theory remains speculative, lacking direct experimental proof. Yet intriguing clues linger. Anesthetics, which selectively switch off consciousness, seem to target microtubules, silencing their quantum vibrations precisely when awareness fades. Some studies even suggest certain anesthetics alter microtubule stability in ways that align with the theory's predictions. The debate stretches beyond science into metaphysics. If consciousness relies on quantum processes, could it exist beyond the brain? Could these microtubule vibrations connect us to deeper layers of reality, as some spiritual traditions suggest? Or is this just wishful thinking, dressing up mystery with quantum buzzwords? While mainstream neuroscience still favors classical explanations, the Penrose-Hameroff theory refuses to fade a testament to the enduring enigma of consciousness itself. After all, if the hardest thing to explain isn't the cosmos out there, but the experience in here, perhaps reality's strangest theory deserves its day in court. Stephen Hawking's greatest revolution wasn't just about what black holes do, it was about what they destroy. In the 1970s, he made a shocking prediction: black holes aren't completely black. They slowly leak radiation, evaporating over unimaginable timescales until they vanish entirely. But here's the catch: according to quantum mechanics, information, the detailed state of every particle that fell in, can never be truly destroyed. So when the black hole evaporates, where does that information go? This is the black hole information paradox, a problem so deep it pits quantum theory against general relativity in a battle for the soul of physics. Hawking initially believed the information was lost forever, erased from reality like a hard drive crushed into dust. This horrified quantum physicists because their entire framework relies on unitarity, the principle that information is perpetually conserved, never created or destroyed. If black holes violate this, quantum mechanics itself might need rewriting. But in 2004, Hawking famously reversed his stance, conceding that information could escape after all, encoded in the Hawking radiation. How? That's where things get messy. One radical solution proposes that black holes don't have serene event horizons as Einstein predicted, but violent firewalls of energy. Imagine approaching what you think is a smooth boundary, only to hit a searing wall of high-energy particles. This firewall would annihilate anything crossing it, preserving information by scattering it back outward as radiation. The math checks out, but the cost is high. Einstein's graceful spacetime curvature gets replaced with a cosmic shredder at every black hole's edge. Worse, it implies an observer falling in would disagree with someone watching from afar about basic physics, a breakdown of objective reality that makes physicists wince. The holographic principle offers a cleaner escape. If black holes store all swallowed information as a 2D hologram on their surface like a cosmic pixelation, then nothing ever truly enters the interior. The information stays safely encoded on the horizon, leaking back out photon by photon over eons. This ties neatly into the AD-S/CFT correspondence, a theoretical bridge linking gravity in higher dimensions to quantum field theories on lower dimensional boundaries. In this view, a black hole's 3D chaos is just a projection of perfectly preserved 2D data. yet mysteries remain. If information escapes, how does it transcend the horizon? Some suggest wormholes threaded through space-time secretly shuttle data back out. Others argue the paradox reveals flaws in our concepts of locality, that particles inside and outside might be entangled in ways we can't yet describe. Whatever the answer, the paradox has become a laboratory for quantum gravity, pushing us toward a theory where space-time isn't the stage, but an actor in the drama, one that might twist, tear, or rewrite its own rules to preserve the universe's deepest secrets. There's a quantum quirk so bizarre it seems to defy logic. What if simply watching something could stop it from changing altogether? This is the quantum Zeno effect, named after the ancient Greek philosopher Zeno of Elea, who famously argued that motion is an illusion. In the quantum realm, his paradox comes to life in the strangest way. A system can be frozen in its current state just by observing it frequently enough. Picture an unstable radioactive atom on the verge of decaying. Left alone, it will eventually break down. But if you continuously measure whether it's still intact, something remarkable happens. The atom stubbornly refuses to decay, as if your attention alone pins it in place. The secret lies in how quantum states evolve. When a system isn't being observed, its wave function spreads out over time, exploring all possible future states like a fog of probabilities. But every measurement forces the system to reset, collapsing the wave function back to its initial state. If these measurements come rapid-fire faster than the system can naturally evolve, it's like hitting pause on reality. The effect isn't just theoretical. In labs, scientists have used lasers to repeatedly check on atoms, effectively trapping them in excited states indefinitely. It's as if the universe has a built-in loophole. Reality bends to the will of relentless scrutiny. This phenomenon isn't just a curiosity, it's a potential game-changer for quantum computing. Qubits, the delicate building blocks of quantum computers, suffer from decoherence, losing their quantum properties when disturbed. But by strategically applying the Zeno effect, researchers could freeze qubits in their desired states, shielding them from errors long enough to perform complex calculations. Imagine a quantum version of a spinning plate act, gently nudging the plates just enough to keep them from falling, except here, the nudges are flashes of light or magnetic pulses that lock information in place. Yet the effect also opens metaphysical trapdoors. If perpetual observation halts change, could an all-seeing observer theoretically freeze the entire universe? Philosophers debate whether consciousness plays a role after all. In quantum mechanics, observation doesn't require a human mind, just interaction with a measuring device. But the line blurs when you consider that devices are built by conscious beings. Does reality, at some level, respond to being watched? The quantum Zeno effect doesn't answer that, but it proves one thing. In the quantum world, seeing isn't just believing, it's creating. And then there's the flip side, the anti-Zeno effect, where frequent observations actually speed up decay instead of preventing it. This happens when measurements are timed to catch the system mid-evolution, like peeking at a melting ice cube just as it's most unstable. Together, these twin effects reveal a deeper truth: quantum systems don't just passively exist. They dance with their observers in a feedback loop where the act of looking becomes part of the story. Whether freezing time or accelerating it, the quantum Zeno effect proves that in the subatomic realm, attention isn't just a spotlight. It's a sculptor's hand shaping what's possible. What if the spooky connection between entangled particles wasn't just a quirk of quantum mechanics, but a hidden wormhole in disguise? That's the startling premise of the ER=EPR conjecture, a radical idea that threads together two of physics' most puzzling phenomena. On one side, you have EPR-Einstein-Podolsky-Rosen entanglement, where particles instantaneously influence each other across vast distances. On the other, Einstein-Rosen bridges, better known as wormholes, the cosmic shortcuts warping spacetime itself. At first glance, they seem unrelated. One's a quantum link, the other a gravitational tunnel. but in 2013, physicists Juan Maldeisner and Leonard Susskind proposed these might be two sides of the same coin, that every entangled pair of particles could be secretly joined by a microscopic wormhole. This idea didn't come out of thin air. It builds on Maldeisner's earlier discovery of the AD/CFT correspondence, a theoretical bridge linking gravity in higher dimensional space to quantum field theories on its boundary. Imagine a hologram where the 3D image emerges from 2D data, except here, the hologram is our universe with gravity and space-time arising from quantum interactions on its edge. AR equals EPR takes this further. If space-time itself is woven from quantum entanglement, then entanglement might literally stitch space-time together, with wormholes as the invisible seams. Picture two black holes entangled at the quantum level. According to the conjecture, their connection wouldn't just be mathematical, it would be geometric, a physical wormhole binding them through folded space-time, even if they're light years apart. Why does this matter? For decades, gravity and quantum mechanics have resisted unification because they speak different mathematical languages. But if entanglement, a quantum phenomenon, creates space-time structure, a gravitational one, it could finally reveal their common grammar. Think of it like discovering that electricity and magnetism aren't separate forces, but aspects of electromagnetism. Suddenly, phenomena that seem disconnected snap into focus. Here, the quantum weirdness of entanglement might encode the architecture of spacetime itself, with wormholes as the glue holding it all together. The implications ripple outward. If ER equals EPR is true, then every time particles entangle, a tiny wormhole forms, not a traversable tunnel you could fly through, but a fundamental thread in spacetime's fabric. This could redefine how we think about black hole information paradoxes. Instead of information vanishing into a singularity, maybe it's secretly transmitted through these hidden wormholes, preserved in the quantum links between particles. Even wilder, it suggests the universe's connectivity isn't just about proximity in space, but about unseen quantum handshakes tying everything together, with wormholes as the hidden wiring behind the cosmic curtain. Critics point out that we're far from proving this conjecture. Wormholes remain theoretical, and the math is abstract, but supporters argue it's too elegant to ignore. After all, if entanglement and wormholes are truly dual descriptions of the same thing, it would mean the universe has been hiding its greatest magic trick in plain sight, that the spooky action Einstein hated is actually spacetime's secret blueprints written in quantum code. And that's a revelation that could rewrite physics from the ground up. Here's the great quantum mystery we've danced around this whole time. Why don't we see cats that are both alive and dead, or baseballs that exist in two places at once? If quantum mechanics insists particles can hover in multiple states simultaneously, why does reality feel so stubbornly definite at our everyday scale? The answer lies in a phenomenon called quantum decoherence, the silent killer of quantum weirdness that explains how the hazy quantum realm gives way to the crisp classical world we recognize. Picture Schrödinger's infamous cat again sealed in its box with a quantum-triggered poison. Quantum theory suggests the cat should exist in superposition, both alive and dead until observed. Yet no one has ever opened a box to find a feline quantum smear. Decoherence steps in to explain why. The instant the radioactive atom interacts with the detector, the vial, the air molecules, or even the cat's whiskers, its quantum state leaks into the environment through countless tiny interactions. These environmental measurements don't require a conscious observer, just random collisions with photons, air particles, or dust motes. Each interaction acts like a pebble tossed into a pond, disrupting the delicate quantum coherence until the superposition unravels entirely. The cat's fate isn't decided by a human opening the box, but trillions of natural processes that collectively collapse the quantum ambiguity long before we peek inside. This isn't just theory, lab experiments confirm it. Isolate an electron in a near-perfect vacuum, chilling it to near absolute zero to minimize environmental noise, and you can preserve its quantum superposition for remarkable lengths of time. But expose it to warmth, light, or even faint magnetic fields, and the superposition crumbles in femtosecons. Scale this up to a cat, a maelstrom of vibrating molecules, chemical reactions, and thermal noise, and decoherence becomes instantaneous. The larger and more complex a system, the faster it surrenders its quantum strangeness to the chattering environment. Critically, decoherence doesn't just explain why we don't see quantum effects in daily life, it reshapes how we interpret quantum mechanics itself. Some argue it replaces the need for wave function collapse, rendering the observer's role purely physical rather than conscious. Others see it as proof that classical reality emerges from quantum foundations through relentless environmental interaction, like how the roar of a crowd emerges from individual voices. Either way, it reveals a universe where quantum magic isn't gone, just drowned out by the noise of existence, hiding in plain sight until we isolate it with heroic experimental effort. So next time you marvel at the oddity of quantum particles, remember, the true miracle isn't that they behave so strangely, but that anything ever behaves normally at all. Decoherence is the universe's way of coaxing order from quantum chaos, one relentless interaction at a time. What if quantum particles could send ripples backward through time to shape their own past? That's the spine-tingling premise of the transactional interpretation, a radical theory proposed by physicist John Cramer in the 1980s. While most quantum models treat particles as waves or point-like objects, Cramer's framework adds a bizarre twist. Quantum events aren't just determined by waves moving forward in time, they're also influenced by waves traveling backward from the future. Picture a quantum handshake where an electron emits an offer wave into the future, and the universe responds with a confirmation wave from the detector it will eventually hit, looping back to complete the transaction. It's as if reality negotiates with itself across time to decide what actually happens. This elegant dance explains one of quantum mechanics' most baffling puzzles, the delayed choice experiment. In these setups, scientists can wait until after a photon has seemingly chosen whether to behave as a particle or a wave before deciding how to measure it. Astonishingly, the photon's past behavior appears to change retroactively based on the future measurement. Cramer's model frames this as a two-way conversation. The photon's offer wave explores all possible paths, while a confirmation wave from the eventual detector travels backward, reinforcing only the consistent outcomes. The result, a self-consistent timeline where past and future co-create each other, like a sculptor refining a statue from both ends simultaneously. Retrocausality, the idea that future events can influence the past, isn't just philosophy here. It's baked into the math. Cramer's equations treat quantum amplitudes as bidirectional, with solutions that explicitly include waves propagating into the past. This sidesteps the need for wave function collapse or observers entirely. Instead, reality emerges from a web of transactions spanning time, each one a closed loop where cause and effect blur. Imagine tossing a pebble into a pond, except the ripples travel both forward and backward, meeting somewhere in the middle to create the splash you actually see. Critics argue this sounds like time travel with extra steps, but supporters counter that it's no weirder than entanglement's spooky action, just more explicit about time's fluidity. After all, quantum mechanics already treats time as malleable. Feynman's path integral formalism sums over every possible history a particle could take. Cramer's insight was realizing those histories might include whispers from the future. The transactional interpretation also tackles quantum weirdness without parallel worlds or consciousness-driven collapse. In Wheeler's cosmic delayed choice experiments, where light from ancient quasars seems to decide its behavior based on present-day measurements, Kramer's model simply says the confirmation waves have been rattling around since the dawn of time, waiting to finalize transactions we initiate now. It's a universe where the past isn't set in stone but in dialogue, a negotiation between what was, what is, and what will be. So next time you flip a quantum coin, remember, the outcome might not just depend on chance, but on a handshake across time itself, an offer made, a confirmation returned, and a reality forged somewhere in between. What if the apparent chaos of the quantum world isn't random at all but the surface ripple of a deeper, hidden order? This is the heart of physicist David Bohm's revolutionary implicate order, a theory that dares to rewrite quantum mechanics by suggesting reality isn't fundamentally fragmented, but an unbroken whole merely unfolding into the world we perceive. While mainstream quantum interpretations grapple with probabilities and collapses, Bohm's framework offers a radically different vision. Beneath the messy quantum dance lies a concealed layer of perfect continuity, where every particle, every force is intimately connected in ways our crude instruments can't yet detect. Bohm's inspiration came from a simple yet profound observation, a hologram. Unlike a photograph where each pixel holds isolated data, a hologram stores the entire image in every fragment. Crack the plate and each shard still reconstructs the full picture, albeit with less clarity. To Bohm, this wasn't just a neat trick of optics, it was a metaphor for the cosmos. He proposed that what we call reality, the explicate order, is just the projected image of a far richer, implicate dimension where everything is enfolded into everything else. Particles aren't separate objects jostling in space. They're transient expressions of this deeper unity, like whirlpools momentarily surfacing in a flowing river. This idea didn't emerge in a vacuum. Bohm was deeply troubled by the fragmentation he saw in both physics and society. Quantum mechanics' reliance on probabilities felt incomplete to him, a mathematical patch over a deeper truth. His hidden variables theory, often dismissed by peers, proposed that particles do have definite positions and trajectories, but they're guided by a quantum potential, weaving through the implicate order like an invisible current. Picture a ship guided not just by its engine, but by the ocean's hidden tides. In this view, entanglement isn't spooky action at a distance. It's two particles responding to the same underlying flow, their correlation as natural as two leaves twirling in tandem on a shared stream. The philosophical allure is undeniable. Where Copenhagen interpretation leaves us with a universe fractured by observation, Bohm's implicate order offers cosmic harmony. Think of a musician hearing a symphony's unity while a novice hears disjointed notes. Our instruments, Bohm argued, are like crude microphones catching only fragments of the grand composition. Even time and space might be explicate illusions, mere projections of a timeless, spaceless implicate reality where past, present, and future coexist like frames in a folded film. Yet the theory faces fierce criticism. Mainstream physicists argue it's needlessly complex, adding hidden layers without predictive advantages over standard quantum mechanics. Worse, Bohm's quantum potential appears non-local, instantaneously influencing particles everywhere, which feels just as spooky as entanglement itself. And without experimental evidence distinguishing it from other interpretations, many dismiss it as metaphysics disguised as physics. But Bohm's legacy endures in unexpected places. His ideas resonate with philosophies from Eastern mysticism to process theology, suggesting a universe more interconnected than reductionist science allows. Modern theories like quantum gravity even flirt with Chinese letter concepts, hinting that spacetime might emerge from deeper, non-spatial relationships. Whether the implicate order is literal truth or poetic inspiration, it challenges us to see reality not as a collection of parts, but as a dynamic, unfolding conversation, one where every quantum whisper might carry echoes of the whole. Quantum mechanics is often presented as a set of ironclad rules governing reality. But what if those rules aren't describing the universe itself, but rather our personal beliefs about it? That's the provocative core of quantum Bayesianism or cubism, a radical reinterpretation that treats quantum probabilities not as objective features of nature, but as subjective degrees of confidence held by individual agents. In this view, the wave function isn't a physical entity out there in the world. It's a mathematical tool in your head, a way to quantify your uncertainty before you take a measurement. Think of it like betting on a coin toss. Before the coin lands, you'd assign a 50% probability to heads, not because the coin is somehow in both states, but because you lack knowledge of its true condition. Cubism applies this logic to quantum systems. When Schrödinger's cat is in its box, you're not describing a superposition of alive and dead states existing in reality. You're expressing your personal uncertainty about which outcome you'll encounter when you peek inside. The moment you open the box, your belief updates, collapsing the wave function in your mental model, not in the universe itself. This perspective sidesteps many of quantum mechanics' thorniest paradoxes. Take wave function collapse. In traditional interpretations, measurement mysteriously forces a quantum system to pick a state. But for cubists, there's no collapse out there. Adjust you, the observer, revising your expectations based on new data. Entanglement's spooky action becomes less eerie, too. If quantum states are personal beliefs, then Alice measuring one particle doesn't instantly alter Bob's faraway particle. It just means Bob's expectations must now align with Alice's results. Yet cubism's subjectivity raises tough questions. If quantum mechanics is all about personal belief, does that mean reality lacks objective structure? Not quite. Cubists argue that while probabilities are subjective, the outcomes we all agree on, the clicks of detectors, the marks on photographic plates, are undeniably real. The framework separates the map from the territory. Your wave function is the map, the territory is the shared world we measure. It's like two detectives working a case. Each may have different hunches, but the evidence they uncover is objective ground truth. Critics push back, arguing cubism risks sliding into solipsism. If science is about uncovering universal laws, how can it rest on personal belief? Supporters counter that all science is inherently observer-dependent. Even classical probabilities reflect our ignorance. What makes cubism radical is its honesty about quantum mechanics' human element. After all, every experiment, every equation, every theory is ultimately filtered through the minds interpreting them. The debate cuts to the heart of what science is. Is physics about discovering a pre-existing reality or constructing useful models to navigate it? Cubism boldly chooses the latter, reframing quantum mechanics not as a cosmic rulebook, but as a language for uncertainty, one where probability isn't a limitation of our knowledge, but the very fabric of how we interact with a universe that remains, at its core, gloriously inscrutable. Imagine standing in a vast cosmic library where every book contains the laws of a possible universe. Most describe worlds too cold, too chaotic, or too empty for life. Yet by sheer happenstance, the one you're holding has just the right equations for stars, planets, and conscious beings like yourself. This isn't fantasy, it's the essence of the anthropic principle, the observation that our universe's fundamental constants appear suspiciously fine-tuned for life's existence. Alter gravity's strength by a fraction, tweak the charge of an electron, or nudge the cosmological constant, and atoms wouldn't form, stars couldn't ignite, and life as we know it would be impossible. The odds of hitting this cosmic jackpot randomly, astronomically low. So why does our universe feel like it was tailor-made? The weak anthropic principle offers a pragmatic answer. If the universe weren't life-friendly, we wouldn't be here to ponder it. In this view, fine-tuning isn't evidence of design, just a selection effect. Our existence filters which universes we can observe. This aligns neatly with eternal inflation's multiverse, where infinite bubble universes sprout with random constants. Statistically, a few will inevitably hit the life-permitting sweet spot, and intelligent observers will only awaken in those. It's the ultimate cosmic lottery where losing tickets go unnoticed. But the strong anthropic principle takes a bolder stance. The universe must allow observers at some point in its history. Some versions flirt with teleology, the idea that life is written into the fabric of reality, as if the cosmos conspires to create consciousness. Proponents point to quantum mechanics' observer-dependent nature, suggesting a feedback loop where life and universe co-create each other. Critics dismiss this as unscientific, but intriguingly, quantum models like Wheeler's participatory universe hint that observation might shape physical laws retroactively, blurring the line between cause and effect. Quantum mechanics adds another layer to the puzzle. If the wave function encompasses all possible outcomes, could our universe's fine-tuned constants reflect a quantum selection process? Some theories propose that early quantum fluctuations didn't just seed galaxies, they chose the laws governing them, with life-friendly configurations stabilizing through decoherence. It's as if the universe conducted a quantum experiment at its birth, collapsing into one of countless possible rule sets, and we're the unlikely outcome. The debate forces us to confront profound questions. Is fine-tuning a fluke a necessity or something even stranger? Whether through multiverse statistics, cosmic destiny, or quantum happenstance, the anthropic principle reminds us that reality's rules aren't just written in the stars, they're deeply entwined with the fact that we're here to read them. And that connection might be the most startling constant of all. What if the universe is sitting on a cosmic tightrope, one wobble away from total annihilation? This nightmare scenario isn't science fiction, it's the unsettling premise of vacuum metastability, a theory suggesting our universe might exist in a precarious, false vacuum state, like a marble balanced atop a hill. The slightest nudge could send it tumbling into a lower energy, true vacuum, rewriting the laws of physics in a cataclysmic chain reaction. The culprit. The Higgs field, the same quantum force that gives particles mass. While we've celebrated its discovery, there's a chilling twist. Calculations suggest this field might not be in its most stable configuration. Instead, it could be trapped in a fragile high-energy state, like supercooled water waiting to crystallize at the slightest disturbance. The math behind this doomsday scenario is terrifyingly precise. If a tiny region of space transitioned to the true vacuum, it would create an expanding bubble of new physics at light speed. Inside this bubble, fundamental constants like the strength of gravity or electromagnetism could change instantly. Atoms might disintegrate, stars would blink out of existence, and the very fabric of reality would unravel, all before any warning. The cosmic reboot wouldn't just destroy life, it would erase the conditions that make life possible anywhere in the observable universe. Strangest of all, this bubble could already be racing toward us from some distant galaxy, invisible until it's too late. Could human activity trigger such an event? CERN's Large Hadron Collider has faced sensationalist claims that its high-energy collisions might create a vacuum decay seed. While physicists universally dismiss this, the energies involved are trillions of times too weak. The research does probe Higgs field behavior under extreme conditions. Some theories suggest cosmic rays or quantum fluctuations could initiate decay naturally, though the probability is astronomically low. Yet low isn't zero over infinite cosmic time. If vacuum decay is possible, the sobering truth is the universe's expiration date might already be set. But here's the counterintuitive silver lining. The fact we exist at all suggests the Higgs field has remained metastable for at least 13.8 billion years. That either means we're safer than the math predicts, or we're living on borrowed time in a universe that's fundamentally unstable. Either way, vacuum metastability forces us to confront a humbling truth. The physics we take for granted might not be written in stone but etched on thin ice, waiting for a quantum whisper to rewrite everything. What if the problems we can't solve aren't just hard, they're windows into deeper layers of reality? That's the startling possibility raised by quantum supremacy, the point where quantum computers outperform classical ones on specific tasks. When Google's Sycamore processor completed a calculation in 200 seconds that would take a supercomputer 10,000 years, it wasn't just a tech milestone, it hinted that some mathematical landscapes might be shaped by undiscovered physics. Take random circuit sampling, the problem Google's quantum chip tackled. While classically simulating these quantum operations becomes exponentially harder with each added qubit, the quantum processor handles them naturally. This divergence isn't just about speed. It suggests quantum systems access computational pathways that don't exist in classical frameworks. Like a fish discovering water only when lifted into air, we might be glimpsing the contours of a reality where computation and physics intertwine at fundamental levels. The implications ripple outward. If certain problems are fundamentally unsolvable classically but tractable quantum mechanically, does that mean mathematics isn't purely abstract but somehow rooted in physical law? Some theorists propose that computational complexity classes might reflect deeper ontological categories, with quantum-accessible problems pointing to phenomena awaiting discovery. Imagine if factoring large numbers, the backbone of modern encryption, isn't just mathematically difficult, but physically forbidden in classical regimes, requiring quantum systems to reach into reality's hidden layers. Critics argue this conflates capability with ontology, that quantum computers simply exploit parallelism classical machines lack. Yet the boundary blurs when considering problems like quantum simulation. Modeling complex molecules exactly often overwhelms classical systems because the quantum correlations involved might literally encode physical phenomena beyond classical description. It's not that classical computers are too slow, they might be fundamentally blind to aspects of quantum many-body physics, like a 2D creature unable to perceive depth. Google's experiments open more questions than answers. If quantum supremacy reveals uncomputable classical problems, might there be hyper-quantum problems only post-quantum systems could solve? Some speculate this hierarchy could continue, with each new computational paradigm unveiling physical layers we can't yet imagine, the unsettling truth. Our mathematical maps might be limited by the physics we know, and quantum computers could be the first tools letting us chart the territories beyond. Time seems like the most universal constant, ticking forward at the same steady pace for everyone, everywhere. But dive into the quantum realm and this intuition shatters. At the deepest levels of reality, where gravity and quantum mechanics collide, time doesn't just behave strangely, it might not exist as a fundamental feature at all. This is the heart of the problem of time in quantum gravity, a puzzle so profound it forces us to reconsider whether the flow of moments we experience is just an illusion painted onto a timeless cosmos. Julian Barber, a physicist with a philosopher's mind, takes this idea to its radical extreme. In his timeless universe, change isn't driven by time's arrow, but by relationships between events. Picture a cosmic flipbook where each page is a static snapshot of the entire universe, a now frozen in configuration space. What we perceive as time's passage is just our brain stitching these snapshots into a sequence, like frames in a movie, creating the illusion of motion. Without an external clock to mark progress, the universe simply is, and what we call time emerges from how these configurations relate to one another. This relational view isn't just philosophical speculation. Einstein's general relativity already dethroned Newton's absolute time, showing that clocks run slower in strong gravity. But quantum gravity goes further, suggesting time might not even be a variable in its equations. Loop quantum gravity, for instance, describes spacetime as a network of discrete grains without an inherent time parameter. The universe's evolution isn't tracked by some master clock, but by how these quantum connections reconfigure, like a sprawling puzzle rearranging itself without reference to before or after. Barber's vision forces us to confront the weight of existence itself. If time isn't fundamental, is the past still real? Is the future already out there in configuration space waiting to be experienced? Some interpretations suggest that every possible now exists simultaneously in a vast landscape of moments, with our consciousness acting like a spotlight, illuminating one at a time. This would mean death isn't an end, just the cessation of that spotlight, while all other moments, including those where you're still alive, remain eternally present in the timeless whole. Critics argue this erases causality, the glue holding physics together. How can you explain why eggs break but never unbreak if there's no time to define earlier or later? Barber counters that causality emerges from the structure of configurations. Certain arrangements logically follow others, creating the appearance of a timeline. It's like reading a novel. The plot unfolds causally, even though every page exists simultaneously in the book. The problem of time doesn't just challenge physicists, it unsettles our deepest intuitions. If Barber is right, the universe isn't a story unfolding in time, but a vast, static tapestry where time is just one thread we've mistaken for the loom. And that realization might be the key to stitching quantum mechanics and gravity into a unified theory, one where time isn't the stage, but a shadow cast by something far stranger. Picture a stadium filled with thousands of spectators watching a race. Each person sees the runners from slightly different angles, yet somehow everyone agrees on who won. This collective consensus mirrors how the universe decides what's real, according to quantum Darwinism, Wojciech's groundbreaking solution to one of quantum mechanics' greatest puzzles. While particles at the quantum level exist in hazy superpositions, the world we experience feels solid and objective. How does this transition happen? The answer lies not in mysterious collapses or conscious observers, but in something far more ordinary: the environment's relentless chatter. Every particle is constantly bombarded by photons, air molecules, and thermal vibrations, countless tiny interactions that act like nature's gossip network. Dirk realized these interactions don't just disturb quantum systems, they select certain states to survive while others fade away. Think of it like a game of telephone played by the universe. Fragile quantum states, like a particle being in two places at once, get scrambled beyond recognition as they pass through the environment. But robust pointer states, states stable enough to leave clear imprints, get copied over and over, spreading their information like wildfire. The more a state is replicated, the more it becomes objective reality, simply because it's the version everyone or every atom agrees on. Take Schrödinger's cat again. In the traditional thought experiment, the cat's fate hangs in quantum limbo until someone opens the box. But quantum Darwinism flips this script. The moment the radioactive atom interacts with the detector, the environment begins measuring it. Air molecules jostle the vial, infrared radiation bounces off the cat's fur, even vibrations in the box's atoms record tiny clues. These interactions aren't careful lab measurements, they're chaotic and random, but collectively they reinforce one outcome over the other, broadcasting the result so widely that it becomes effectively irreversible long before a human peeks inside. This explains why we don't see quantum weirdness in everyday life. A baseball flying through the air isn't in multiple places at once because trillions of photons scatter off it every second, each collision voting for a single position. The baseball's location isn't magically collapsed by our eyes, it's democratically elected by the environment. Even in a vacuum where we might expect quantum effects to linger, residual heat and cosmic background radiation ensure no particle stays isolated for long. Decoherence isn't a flaw, it's the universe's way of tallying votes until reality emerges as the majority report. Lab experiments have caught this process in action. In controlled setups, scientists can watch fragile quantum superpositions unravel as they interact with even a handful of stray particles. The finer the measurement, the faster the consensus forms. It's as if reality isn't decreed by physics, but negotiated through countless tiny transactions, a marketplace where only the most tradable states survive. The philosophical implications are profound. If objectivity arises from environmental gossip, does that mean reality is at its core a social phenomenon? Not quite. While our classical world feels solid, quantum weirdness still lurks beneath the surface, visible only when we isolate systems with heroic effort. Quantum Darwinism doesn't erase the strangeness, it just explains why it's so hard to see. In this light, the universe isn't a static stage but a dynamic network of relationships where what we call real is simply the story that's been copied enough times to stick. And that story is still being written, one quantum interaction at a time. Some of the fiercest battles in physics aren't fought in labs, they're waged in thought experiments where titans like Stephen Hawking and Leonard Susskind clash over the fate of reality itself. The Black Hole War, as it came to be known, began with Hawking's explosive claim in 1976. When black holes evaporate, they don't just vanish, they take information with them, erasing it from the universe forever. This wasn't just a technical quirk, it struck at the heart of quantum mechanics, which insists information can never be truly destroyed. To lose it would be like burning a library and finding the ashes contain no trace of the book's words. A violation so profound it threatened to unravel physics itself. Susskind, Hawking's intellectual rival, refused to accept this cosmic censorship. For decades, they traded equations and barbs, with Hawking famously conceding the debate in 2004, but only after Susskind and others armed themselves with a revolutionary weapon, the holographic principle. This radical idea suggested that every bit of information swallowed by a black hole isn't lost in its crushing depths, but smeared like quantum graffiti across its two-dimensional event horizon. Imagine dropping a snow globe into a pond. In Hawking's original view, the globe shatters and disappears forever. But the holographic principle argues the pond's surface ripples encode the globe's exact shape, a frozen hologram preserving every flake's position, waiting to be decoded. The resolution reshaped quantum gravity entirely. If black holes preserve information holographically, then spacetime itself might operate like a cosmic hard drive, with three-dimensional reality emerging from a deeper two-dimensional code. This wasn't just about saving data. It hinted that gravity, the curvature of spacetime, might emerge from quantum entanglement patterns on this hidden surface. Picture a woven tapestry. From afar, you see images and depth, but up close, it's just threads crossing in flat, intricate relationships. Similarly, our 3D universe could be the image projected from entangled quantum threads we can't yet see. Hawking's surrender came with poetic irony. He showed that black holes do leak information back out, not in some orderly stream, but scrambled into quantum noise like a shredded document reassembled by a madman. Yet the mere possibility of retrieval was enough. The episode didn't just settle a bet, it revealed black holes as cosmic Rosetta Stones, their event horizons translating quantum mechanics and gravity into each other's languages. Today, this holographic bridge fuels theories from string theory's add S/CFT correspondence to loop quantum gravity's spin networks, proving that sometimes physics' fiercest wars birth its most unifying peace treaties. What if a particle could leave its own properties behind, like a ghost abandoning its shadow? This eerie possibility isn't science fiction, it's the quantum Cheshire cat effect, a phenomenon where particles seem to separate from their physical attributes, leaving behind a grin without a cat. The name, of course, nods to Lewis Carroll's mischievous feline, but the science behind it is even stranger than the Wonderland tale. In 2013, researchers designed a mind-bending experiment to test whether a neutron spin, a fundamental property like its magnetic orientation, could be detected in a different location than the neutron itself. The results defied classical intuition. The particle's spin and its physical presence appeared to occupy separate paths, as if the neutron had ditched its own identity like a discarded coat. The experiment relied on the delicate art of quantum interference. Neutrons were sent through an apparatus where they could take one of two possible routes, much like the double-slit setup. But here's the twist. Cleverly placed filters and detectors allowed scientists to measure the neutron's spin in one path while detecting the particle's position in the other. The outcome, the neutron's physical mass registered in one place, while its spin, what you'd think was an inseparable part of it, showed up somewhere else entirely. It's as if you weighed a suitcase in London but found its contents mysteriously appearing in Paris. This isn't just a quantum magic trick. The Cheshire Cat effect forces us to confront an unsettling question: what is a particle if its properties can wander off on their own? In classical physics, an object's traits are glued to it. A bowling ball can't ditch its weight or a magnet its polarity. But in the quantum realm, properties like spin, charge, or even momentum might not be hardwired to particles so much as loosely tethered, capable of being teased apart under the right conditions. Some interpretations suggest these disembodied properties are still subtly connected through quantum contextuality, a fancy way of saying that the act of measurement defines what's real in that moment. Critics argue the effect is more about semantics than substance. The neutron isn't truly splitting from its spin, they say. It's just that quantum measurements can selectively reveal different aspects of a system, creating the illusion of separation. After all, quantum mechanics has always been fuzzy about where properties live. But supporters counter that the Cheshire Cat experiments expose a deeper truth. Properties might not be inherent to particles at all, but relational features that emerge from interactions. Think of it like a game of peekaboo. The smile isn't on the cat until you look for it. The implications ripple into foundational debates. If particles and their properties can part ways, does that mean physical reality is less like a collection of objects and more like a network of fleeting relationships? Could this explain why quantum systems resist classical descriptions, because their very essence is context-dependent, shifting based on what we choose to measure? The Cheshire Cat effect doesn't offer easy answers, but it does something far more valuable. It reminds us that quantum mechanics isn't just breaking the rules of reality. It's showing us that the rules we thought existed were only ever illusions, and the truth is far more whimsical and far more puzzling than we ever imagined. Imagine tossing a coin, then waiting a full minute before deciding whether to catch it mid-air or let it land. And somehow, your delayed choice determines whether the coin was spinning heads or tails before you even made the decision. This isn't just a thought experiment, it's the essence of the delayed choice quantum eraser, a real-world setup so baffling it makes time itself seem like a tangled knot. At its core, this experiment reveals a truth stranger than fiction. Particles don't just respond to present observations. They might retroactively adjust their past behavior based on future measurements. The setup builds on the classic double-slit experiment, where particles like photons create wave-like interference patterns when their paths aren't observed. Add a quantum twist. After a photon has already passed the slits, but before it hits the detector, scientists use beam splitters and mirrors to erase or preserve information about which path it took. Here's where it gets surreal. If the path information is erased after the fact, the photon suddenly resumes behaving like a wave, producing interference as if it had traveled both paths all along. But if the path is recorded, the photon acts like a particle, as if it knew its history would eventually be scrutinized. This isn't just quantum weirdness, it's a direct challenge to causality. John Wheeler, who first proposed the delayed choice idea, saw it as evidence that reality isn't fixed until questioned. Picture a cosmic game of 20 questions where the universe doesn't just answer, it retroactively writes the answers into history. In 2007, scientists took this further, using light from distant quasars that had traveled billions of years to decide today whether those ancient photons behaved as particles or waves. The implications are staggering. Choices made now might ripple backward, rewriting quantum events that predate human civilization. Critics argue this doesn't mean time flows backward, just that quantum systems remain unsettled until final measurement. But supporters see deeper mysteries. If future choices shape the past, does free will exist, or are we just unraveling a predetermined tapestry? Some interpretations suggest the universe avoids paradox by branching into parallel timelines, while others propose a block universe where past, present, and future coexist statically. The delayed choice eraser doesn't just blur time, it erases the line between cause and effect, leaving us with a universe that doesn't play by classical rules. It's as if reality isn't a story written in stone, but a script constantly edited by its own audience, one where the ending might just rewrite the beginning. You've probably noticed how a steaming cup of coffee cools gradually, predictably, following the laws of thermodynamics we all learned in school. But in the quantum realm, even something as familiar as cooling can take a bizarre turn. Enter the quantum Mpemba effect, a phenomenon where certain quantum systems don't just cool faster than expected, they can cool faster when they start hotter, flipping classical intuition on its head. The name nods to a teenage Tanzanian student, Erasto Mpemba, who noticed in the 1960s that hot water sometimes freezes quicker than cold, a counterintuitive observation that puzzled scientists for decades. Now, quantum physicists are uncovering something even stranger. Under precise conditions, quantum particles can shed heat in ways that make no sense in our everyday world. Recent experiments with trapped ions, charged atoms held in place by electromagnetic fields, reveal this effect in action. When these ions are prepared in carefully tuned quantum states, researchers have watched as hotter systems reach equilibrium faster than their cooler counterparts. It's as if a scorching pan left on the counter chilled to room temperature before a lukewarm one, defying the classical expectation that cooling is a monotonous step-by-step process. The secret lies in quantum shortcuts, specific pathways through the energy landscape that only become accessible when the system starts in a high-energy or hotter state. Think of it like hiking down a mountain. The classical route winds slowly along switchbacks, but the quantum version might reveal a hidden ravine only visible from certain elevations, offering a steep, direct descent. This isn't just a curiosity, it could rewrite the rules of quantum thermodynamics, a field exploring how heat and energy behave at the smallest scales. In classical thermodynamics, systems evolve toward equilibrium predictably, with hotter objects always taking longer to cool than colder ones. But quantum mechanics introduces a wild card, coherence, the delicate property allowing particles to exist in superpositions of multiple states. When a quantum system is prepared with coherent energy states, its path to equilibrium isn't just about losing heat, it's about how those states interfere with each other along the way. Hotter systems with more energy to redistribute can exploit constructive interference to shed energy in sudden, coordinated bursts, while cooler systems plod along incrementally. Practical applications shimmer on the horizon. Quantum computers, plagued by overheating qubits, might one day leverage this effect to cool critical components faster, sidestepping the thermal bottlenecks that currently limit their performance. Or imagine quantum engines, microscopic devices that convert heat into work designed to exploit these accelerated cooling pathways, achieving efficiencies impossible in classical designs. Some researchers even speculate that the quantum Mpemba effect could play a role in biological systems, where quantum coherence might subtly influence how enzymes manage energy transfer. Yet mysteries linger. Why do only certain quantum systems exhibit this behavior? How does decoherence, the breakdown of quantum superpositions, disrupt these cooling shortcuts? The answers could reshape our understanding of how quantum systems evolve, blurring the line between the familiar world of thermodynamics and the surreal domain of quantum mechanics. One thing's certain, in the quantum realm, even something as mundane as cooling down isn't just a matter of physics, it's a dance of probabilities, where heat doesn't always fade predictably, but sometimes vanishes in a quantum leap. Have you ever been convinced something happened a certain way only to discover most people remember it completely differently? This unsettling sensation lies at the heart of the Mandela effect, where large groups share vivid but false memories, like Nelson Mandela dying in prison he didn't, or the Monopoly man wearing a monocle he never did. But what if these discrepancies aren't just faulty neurons? Some theorists propose something far stranger, that these collective false memories could be echoes of alternate timelines bleeding into our reality, courtesy of the quantum multiverse. In the many worlds interpretation, every decision spawns parallel universes, infinite versions of history branching like a cosmic kaleidoscope. Most branches remain forever out of reach, but quantum mechanics leaves room for subtle crossovers. Imagine two neighboring timelines where, say, a famous movie quote was slightly different. If quantum fluctuations momentarily bridged these worlds, could fragments of the other version imprint on some minds, creating a splintered memory shared by thousands? Proponents point to cases like "Luke, I am your father," a misquote so pervasive it overshadows Darth Vader's actual line, "No, I am your father." To believers, this isn't mass confusion, but a subconscious whisper from a universe where the line really was spoken that way. Psychologists, however, offer a less cosmic explanation. Our brains are prediction machines, constantly editing memories to fit familiar patterns. When we hear, "I am your father," our minds auto-correct it to match the more dramatic cadence of movie tropes, stitching the error into recollection. The Monopoly man's monocle, a classic case of schema-driven error. We associate old-timey capitalists with monocles like Mr. Peanut, so we retrofit the image. Studies show memories morph over time, especially when reinforced by social contagion. One person's misremembered detail repeated online can spread like a cognitive virus. Yet the quantum hypothesis lingers because it taps into a deeper unease. Why do these false memories feel so real to those who experience them? Unlike typical illusions, Mandela effects often carry emotional weight, a visceral certainty that clashes with documented reality. Some researchers speculate quantum processes in the brain, like Penrose Hameroff's microtubule vibrations, might make consciousness sensitive to cross-timeline interference. It's a stretch, but not impossible. If space-time is fundamentally quantum, perhaps minds occasionally tune into alternate histories like radios picking up faint signals. The debate crystallizes a fundamental tension between a universe where reality is fluid and participatory, and one where human perception is simply fallible. Both explanations acknowledge memory is reconstructive, not photographic. But where psychology sees a glitch, quantum speculation sees a feature evidence we're navigating a multiverse where truth is more layered than we dreamed. Maybe the truth lies somewhere in between, a world where brains do misremember, but quantum weirdness occasionally nudges those errors into uncanny alignment. After all, in a universe this strange, who's to say reality isn't whispering to us not just through facts, but through the cracks between them? Could the universe's final act be not a cold, silent fade to black, but a cosmic encore where every consciousness that ever lived is resurrected in a quantum afterlife? This is the audacious claim of physicist Frank Tipler's omega point theory, a fringe idea blending cosmology, quantum mechanics, and theology into a vision so grand it rewrites the meaning of existence itself. Tipler's argument begins with a startling extrapolation of known physics. As the universe collapses toward its final singularity, the omega point, computational power and information density would theoretically approach infinity. Under these extreme conditions, he proposes, an omnipotent quantum intelligence could emerge, harnessing infinite energy to simulate every possible mind that ever existed, effectively reviving the dead in flawless digital recreations. It's a notion that straddles the line between scientific speculation and metaphysical revelation, one where the laws of physics become the machinery of immortality. The theory's scientific scaffolding borrows from relativistic cosmology and quantum information theory. Tipler calculates that in a closed universe, one destined to recollapse under gravity, the exponential increase in energy density near the end would allow for infinite computation cycles within finite proper time, a phenomenon akin to a cosmic computer booting up near the singularity. This intelligence, having absorbed all knowledge, could then reconstruct any historical person's consciousness atom for atom using quantum data preserved in space-time structure. Think of it as the ultimate backup drive, the universe's final moments acting as a divine retrieval system for lost souls. Critics pounce on multiple fronts. The omega point relies on a recollapsing universe model, but current observations suggest cosmic expansion is accelerating, making a big crunch unlikely. Even if the math holds, the leap from infinite computation to conscious resurrection raises philosophical red flags. Can a simulation truly be you, or just a copy wearing your memories? And who or what would govern this quantum god's ethical choices? Theological tensions simmer too. By framing resurrection as a physics inevitability rather than divine miracle, Tipler's theory courts accusations of scientism attempting to reduce sacred mysteries to equations. Yet the idea's resonance persists because it mirrors ancient eschatological themes through a quantum lens. The omega point's infinite intelligence echoes Teilhard de Chardin's theological concept of the same name, a convergence of all consciousness toward divinity. Even secular transhumanists find glimmers of hope in the notion that physics itself might guarantee a form of immortality. The theory's power lies in its audacity. It doesn't just predict the universe's end, but reimagines it as a cosmic redemption story written in the language of wave functions and entropy. Beneath the controversy, Tipler's vision forces us to confront the deepest questions. If consciousness is truly an information pattern, could physics one day preserve it beyond biological death? Does the universe's arc bend toward meaning, or is that just a story we tell to soothe our mortality? The omega point theory may remain fringe, but its radical hope lingers, that in the quantum scribbles of spacetime's last seconds, every laugh, every thought, every love might flicker back to life, not as metaphor but as physics. And that possibility, however remote, changes how we see our place in the cosmic dark. From parallel worlds branching with every decision to entire universes encoded like holograms on a 2D surface, the quantum realm doesn't just bend the rules of reality, it shatters them entirely. We've journeyed through theories where particles communicate faster than light, where time itself might be an illusion, and where consciousness could shape the fabric of existence. And here's the breathtaking part: none of this is science fiction. These are serious scientific frameworks, each grappling with the same quantum mysteries from wildly different angles. Some theories, like the many worlds interpretation, paint a cosmos of infinite possibilities where every choice spawns new timelines. Others, like the holographic principle, suggest our 3D reality might be a shadow cast by information flickering at the universe's edges. Then there's the simulation hypothesis, which asks whether we're living in an advanced civilization's quantum computer, a notion that turns the very nature of existence into an open question. And let's not forget the mind-bending implications of quantum Darwinism, where reality itself emerges from a kind of cosmic consensus, voted into being by countless interactions we barely notice. What's astonishing isn't just the diversity of these ideas, it's how they force us to rethink what science is. Quantum theories don't just describe the universe, they blur the line between physics and philosophy, between observation and creation. They challenge us to consider whether time is fundamental or emergent, whether particles are objects or relationships, and whether the universe is a fixed stage or a participatory drama where we're both audience and actors. So, which theory resonates with you? Do you find comfort in the orderly branching of the multiverse, or does the holographic principle's illusion of depth speak to your curiosity? Maybe you're drawn to the eerie elegance of entanglement, where particles whisper secrets across light years as if space and time don't matter. Whatever your favorite, one thing's certain: the quantum world is stranger than we ever imagined, and the journey to understand it is far from over. If your mind is buzzing with questions or theories of your own, drop them in the comments below. There's nothing more thrilling than debating the nature of reality with fellow explorers. And if you're hungry for more deep dives into the cosmos' greatest mysteries, hit that subscribe button, because the universe isn't just full of secrets, it's waiting for us to ask the right questions. And who knows, the next big breakthrough might just come from a curious mind like yours.